So let's see how to solve for uh, competitive equilibrium. Okay, so let's do a problem. Okay, and let's slowly solve. By taking each and every step. Carefully. Let's solve for Pareto efficiency as well as competitive equilibrium, and then I'll also tell you how to do that graphically. You can actually solve for competitive equilibrium graphically as well. And it's very quick. Okay, so I'll also tell you about that. Okay, first let's do a problem, and what we are going to do is we'll find the Pareto efficient allocation. Okay, and we'll also figure out the competitive equilibrium in the same economy. Okay, so suppose utility of Robinson Crusoe is URC equals R times C. Okay, and suppose the production function is C equals F of L equals L. Okay, let's do a very simple example. Okay, this is a linear production function, and this is the Cobb-Douglas utility. Okay, so if you plot the picture, okay, if you plot the picture of the production function, this is how it's going to look, right? And what is the slope of this line? -1, right? Okay. Okay. So the objective is to choose a point on this line that maximizes the utility, right? I mean, that's if you want to find efficient allocation, you have to choose a feasible allocation that maximizes the utility of the only consumer in this economy, Robinson Crusoe, right? So, what is the objective? Maximize with respect to, right? This is the problem that you want to solve, right? And here F is, okay. So notice that this particular problem can be reduced to a problem like this: maximize RC belonging to R2 plus. Okay, so C can be written as 1 minus R. So C plus R equals to 1, right? I mean, I can write this as C plus R equals to 1, right? Constraint. Okay, and RC, right? Do you agree I can just reduce this problem by eliminating one of the variables, L, because I know that R plus L is 1. So by eliminating one of the variables, I can just reduce this problem to a two variable optimization problem, right? Yes or no? And solving this problem is very easy because if you see, this is a standard Cobb-Douglas environment, with a linear constraint. So you can easily do it, and you'll get R equal to half and C equal to half. Okay, and since C equals L, so L is also half. So the Pareto efficient allocation is this, right? Yes or no? CP RPLP is half, half, half. Right? Yes or no? Is this clear? Everybody? Yes or no? Is that okay? Okay, now let's find competitive equilibrium. So how will you find competitive equilibrium? So while you are finding competitive equilibrium, so this is how you're going to approach the problem. You're going to first solve the profit maximization problem of the firm. The reason why you solve the profit maximization problem first is because, as I've told you, that the profits in the definition, as you have seen in the definition, the profits that the firm earns, they are part of the budget of the consumer, Robinson Crusoe. So it is advisable to solve the profit maximization problem first. Okay. So what is the profit maximization problem? Maximize with respect to CL in R2 plus C minus WL, okay, subject to the constraint that C is less than or equal to L. Right? This is a profit maximization problem. Yes. Okay. So it's actually a very simple problem. But let's just quickly see how to actually think about this particular problem. So I'll also give you at the same time the picture, okay, because I think it's going to be useful, to draw the picture. Okay. So when you're going to solve this problem, okay, notice that Robinson Crusoe as a firm doesn't care about the physical constraint of the labor time. Okay, so you can choose any amount of labor, right? So you can choose any amount of labor in this direction. Okay, so what I'm going to do is I'm going to draw iso profit curves. I'm going to draw iso profit curves. So what are iso profit curves? Please note that this is not the only way to do it. There are other ways to do this problem as well. But I want to do it this way because this actually helps you to also get the graph right. Okay, because it also gives you the graphical approach. Okay, so let me talk about that. So what I'm going to do is I'm going to draw iso profit curves. So what are iso profit curves? Iso profit curves are the combination of C and L such that the profit is constant. C minus WL equals to a constant profit. Okay, fine. So if you want, you can just write it as pi bar or something, you can just, okay. So that's an iso profit curve. Okay, so let's draw an iso profit curve. So notice that if I want to draw an iso profit curve for profit equal to 0, so let's draw an iso profit curve for profit equal to 0. Can you tell me how is that going to look? Okay, let's assume that W is less than 1. Suppose W is less than 1. How is the iso profit curve going to look? Let me use the red color.
It'll be below the production function. It'll be below the production function.
That's right. It will be like this, right? Do you agree? Notice that this point will be there because at this point L is 0, C is 0. Okay, so it will pass through this point. And what will be the slope of this? Slope will be
W, sir.
W in absolute terms. Is that okay? And what is the absolute value of the slope of this curve? It's 1. Okay. Now, what about this point? What do you think is the profit at this point? Is this more than this or less than this? Is this more than 0 here or less than 0? What about the profit at this point? What do you think? So if I draw another iso profit curve,
So it would probably lower, sir, because W is more than 1. I mean, this assumes W is equal to 1. So
no,
probably
no, no, no,
it
no, no,
would.
no, no.
Okay.
Notice that these iso profit curves are parallel to each other. These iso profit curves are parallel to each other. All of them have the slope W. So if I draw another iso profit curve, this will be an iso profit curve which will be parallel to the other iso profit curve. So these are parallel to each other. I am asking whether this is a higher iso profit curve or a lower iso profit curve, whether this will give you higher profit or lower profit. That is what I'm asking. And the answer is that it will give you higher profit. Why is that going to be the case? Because if you see over here, what is this intercept? What is this intercept? At the intercept, L is 0, right? At the intercept, L is 0, right? So notice that when L is 0, C is pi bar. So, and since it's a positive intercept, your pi bar is positive. And can you make higher profit? The answer is yes. You can make even higher profit if you choose this point. It will be on an even higher iso profit curve. Can you make even higher profit? Yes, you can make even higher profit if you choose a point like this. Now the question is, does the solution to the profit maximization problem exist in this problem? Does the solution to the profit maximization problem exist in this problem?
The
When W is less than 1.
maximum L can be one only. I mean, this blue line, like
No, no, no.
it's
But remember, from for the firm, this
okay,
is not a
okay.
constraint.
Yeah, okay.
So the question is, does the solution to the profit maximization problem exist for the firm in this case? The answer is no. Because you can keep going up in this direction, you keep earning more and more profit. Yes or no? Is that okay? Your profit will keep going up, right? You keep moving up on the production function, keep getting more and more money, right? Keep earning more and more money. And there is no maximum, there is no point where the profits are maximized, right? Because you can make infinite profits here. Is that okay? Have you understood this? So solution to this problem does not exist when W is less than 1. Okay. So now there are only two cases which are left. One is W equal to 1, and then W is greater than 1. So let's just do those two cases as well. Let's figure out the optimal choice of the firm in those two cases. Okay. Okay, now when W is equal to 1, C equal to L, C minus L equal to 0 is also the isoprofit curve, right? I mean, this production function is also the isoprofit curve corresponding to zero level of profit, right? Now, can you make more money than this? Can you make more money than zero profit in this case? Is there any point on the production function which lies on this isoprofit curve? You want to maximize profit, right? So you want to climb to the highest possible isoprofit curve that passes through the production function. So is this possible that you can make this much money with this production function? Not possible, right? Because there is no intersection of this isoprofit curve with this production function. Do you agree? So the highest possible isoprofit curve that can pass through the production function is the isoprofit curve corresponding to zero level of profit. So basically you can make zero profit, and zero profits are your maximum profit. Okay, uh, by choosing any point on the production function. Okay, so solution does exist in this case. Okay, solution to the profit maximization problem does exist in this case. And what is it? What is the solution? So basically this entire line. Okay, so all these are solutions to the profit maximization problem. And what about if W is less than 1? Sorry, what about if W is greater than 1? And notice that the optimal profit will be 0 in this case. Optimal profit is 0. Notice that in this case, your highest possible isoprofit curve will look like this. And these are going to give you negative profits, or basically losses. All these other points will give you losses because the intercept is in the negative direction, right? The intercept is below the horizontal axis. So the profit will be negative at all these points. So the profits are maximized at this point because this is the highest possible isoprofit curve that passes through the production function. Is that okay? So in case of W greater than 1, in case of W greater than 1 also we have C equals L equals 0 as a solution. Okay, and optimal profits are still 0. Is that clear to everyone? Okay, now let us think about Robinson Crusoe as a consumer. Okay, now Robinson Crusoe as a consumer will solve the following problem, which is maximize RC by choosing RC in R2 plus subject to the constraint that C is less than or equal to W times 1 minus R plus the optimal profit. Notice that W less than 1 is ruled out, because in W less than 1 this solution does not exist. So we cannot have a competitive equilibrium for the case where W is less than 1. So we can only consider the case where W is greater than or equal to 1. And in case of W greater than or equal to 1, the optimal profits are 0. In both these cases, optimal profits are 0. So I can completely ignore this. Is that okay? I can completely ignore this. And what I'm going to get is that this is one of the constraints. And then, of course, we also have this constraint that R must be between 0 and 1. Now, if you just look at this, just stare at this. Optimal profit is 0. C less than or equal to W1 minus R. What is the boundary of this constraint? It is only this, right? This is the boundary of the constraint. So when W is equal to 1, it is the constraint that you have to pick a point on this line, right? Because what is this line? This is C equal to WL, right? C equal to WL line, right? Because C minus WL equal to 0, right? And here also it is C minus WL equal to 0. So this red line is C minus WL equal to 0 line here. And here also this red line is C minus WL equal to 0. Right? So if you see, this constraint is nothing but C equal to WL, the boundary of the constraint, of course, is nothing but C equal to WL. Yes or no? And since R is between 0 and 1, so we just have to restrict ourselves up till this point. We cannot go beyond this point. So it's the red line. Basically, it's the highest possible ISO profit curve, which is your budget constraint, which is your budget line. Okay. Restricted to this region only. So even in this case, it will be this. Is that okay? That's your budget line from here till here. Yes or no? In case of W greater than 1, it is from here to here. In case of W equal to 1, it is from here to here. Yes or no? That's your budget boundary. Do you agree? So the budget boundary is nothing but your highest possible ISO profit curve restricted to R between 0 and 1. Is that okay? Or L between 0 and 1. Have you all understood this? Is that okay? So please reply. If it is not clear, you can ask.
So, like, why won't it be an addition of the blue and the red lines?
What do you mean by addition of the blue and the red line?
Like, this is C is at most W into 1 minus R, and then plus that 0 profit.
Yeah.
So, won't we
So
account
C.
for
So
the
so what is this? This is L, right? You can think of this as L, right? 1 minus R is L, right?
L? Okay, from there, then, okay, we get
So
it.
C is less than or equal to WL, right? That's it.
Okay.
So what is the boundary of this? C minus WL equal to 0, right? That's the boundary.
Yes, sir.
Okay. So that is what I'm saying, that this is your highest possible ISO profit curve is actually your budget line also.
Okay. Yes.
Okay. So this is your highest possible ISO profit curve in the case where W is greater than 1. And this is your highest possible ISO profit curve in case when W is equal to 1. So in case of W greater than 1, this is your budget line. In case of W equal to 1, this is your budget line. Is that fine now?
Yes, sir. Yes.
Okay. Now all that you have to do is, so you can easily see over here that this cannot be this. W greater than 1 is not possible. The reason is because if W is greater than 1, Robinson Crusoe as a consumer will choose a point like this. and the firm has chosen a point like this, right? Firm chooses this point and the consumer will choose this point. So that can never be an equilibrium, right? Because there is a difference between what firm is choosing and what the consumer is choosing. Firm is saying that, okay, I don't want to hire any labor, I don't want to produce any coconuts. Consumer will say that I want to consume coconuts and I want to supply labor. So that's clearly a mismatch of what firm wants and what the consumer want, right? Yes or no? And we can also solve it and get it. We can just solve this and get it. It's not a big deal. Maximize RC in R2 plus RC, and this thing can be written as C plus WR less than or equal to W. Okay. So what are we going to get? We are going to get R equals W by 2W, which is half. And this implies that L is equal to half. And clearly, when W is greater than 1, R is half, L is half. But if you see, when W is greater than 1, L is 0. Okay, so this is your labor demand. Labor demand is 0. Coconut supply is 0. And this is your labor supply. Labor supply is half. And coconut demand is, W by 2. Okay, so clearly there is a mismatch, when W is greater than 1. And this is kind of obvious from the picture, because if you see, given this budget line, Crusoe will choose a point here. He's not going to choose this point. This is on a lower indifference curve for Crusoe. This is the highest indifference curve passing through the budget line. And firm has chosen this point. Crusoe is choosing this point. So obviously there is a mismatch between demand and supply, right? Yes or no? Firm is choosing a different point. Crusoe is choosing a different point. So clearly, that can never be the equilibrium. But when W is equal to 1, when W is equal to 1, then firm can choose any point. There is no problem, because every point here is profit maximizing and is also feasible. Okay. So firm can choose any point here. Here, the unique profit maximizer was this, but here there are multiple profit maximizers. Everything is profit maximizing. So whatever Crusoe chooses, we can make the firm choose exactly that point. So this is the competitive equilibrium. Have you all understood this? When W is equal to 1. And this is the point which is also Pareto efficient, because this is exactly the point where L is half, C is 1 by 2, and R is also half. That's the efficient point. Is this clear? So that's your competitive equilibrium.